Okay, so here we are. This is the third piece of the renal lecture, and we've already talked about glomerular filtration. We've talked about reabsorption of salt and water. And now what I want to talk about is a little bit of reabsorption of glucose specifically. And then we'll talk about tubular reabsorption, and then we'll spend some time discussing aldosterone. Okay, so generally speaking, all of the glucose is going to be reabsorbed. Right? So remember, glucose is a very important commodity in your body. You really, really want that glucose as much as possible so that you can get a lot of ATP and do a lot of cellular work. So your body is going to reabsorb all of the glucose under most circumstances. Okay, so in the proximal convoluted tubule, because glucose is polar, okay, because it's polar, it's going to do a two-step process, and both of them are going to rely on carrier proteins, right? So it'll do co-transport, which is a form of secondary coupled transport, and it'll co-transport along with sodium. Okay, so it'll use the sodium to help bring the glucose into the cell as well. This is exactly the same scenario that we already talked about when we talked about coupled transport in that lecture. Okay, so we'll use coupled transport to bring the glucose into the cell, and then from there we're going to use facilitated diffusion, this one over here. We use facilitated diffusion to put that back into the extracellular space and then into the blood supply. Again, once it's in the bloodstream, it can just go inside the bloodstream and be carried around wherever it needs to go. Okay, so most important piece of information from the slide, all the glucose is getting taken back in. Now let's talk about what happens with diabetes. So for diabetes, the amount of glucose in the blood is very, very high because without insulin or with insulin insensitivity, you're unable to get the glucose into the cells because you don't have glucose transports in the cells of the body, so they can't bring it in. And if the cells can't bring the glucose into them, it's going to be very high in the blood. It'll just be left in the blood. And so that means that when you're filtering the blood at the glomerulus, you're going to have a ton of glucose in the filtrate. Okay? Now, generally, you're going to have some carrier proteins that help reabsorb that glucose back into the body. But like all carrier proteins are subject to saturation. Okay, so that means that they can only reabsorb a certain amount of glucose, and after that point, there's nothing that can be done. Okay, so if you increase the amount of the glucose, at some point they will become saturated. Working as fast as I can, man, can't get any more in there. Okay, so if you have diabetes, you have glycosuria, which just means glucose in the urine. And that just means that does not mean that your glucose carrier proteins are anything wrong with them. They're still functioning perfectly fine. They're just saturated, so they're unable to reclaim all of the glucose. So some of it gets left behind, and then it'll be excreted out of the body in the urine. Okay, so again, functional, perfectly happy glucose carrier proteins. They're just saturated. Okay, on to tubular secretion, but it's only one slide. So remember that reabsorption back into the body, secretion is just the opposite of that. And what we're going to do is anything that we weren't able to go through the filtration, but we still need to get rid of it, things like drugs or toxins or anything we don't want. Now we're going to use active transport to put it into that, into the tube so that we can excrete it. Okay, so it's just the opposite of reabsorption. That's enough about that. Okay, so now let's talk a little bit more about how you regulate the amount of salt reabsorption. Okay, so up to this point, most of our focus has been on water reabsorption, and we've only talked about salt reabsorption in the context of creating an environment that helps us reabsorb water. Now let's talk about how we regulate how much of that salt we bring back into our bodies. And that's going to be regulated using aldosterone. Okay, so do you remember aldosterone? Aldosterone is going to be secreted from the adrenal gland, the adrenal cortex. It's a mineral corticoid, which means that it comes from the adrenal cortex and it regulates mineral balance. And so the way that it works is it's going to regulate the amount of additional salt that you need, right? So you're going to have a fairly consistent level of salt in the proximal convoluted tubule and the loop of Henle. You'll have a constant regular, so you always get that much salt. Okay, so about 90% of the salt will come back. But in the distal convoluted tubule and the collecting duct, so those last two little segments of the tubule, now what you get to do is you get to vary how much additional salt comes back in, and how much additional salt you're going to reabsorb is going to depend upon the current need in the body. Okay, so if you have low sodium, that's going to cause the secretion of aldosterone, and the secretion of aldosterone is going to help increase sodium absorption at the expense of potassium. So you'll lose potassium in the urine, but you get to keep more of the sodium, and that's the main point. You have too low sodium, let's get more sodium into the body using aldosterone. The mechanism of action for the aldosterone is to activate the sodium-potassium pumps. And these are the same sodium-potassium pumps that we talked about when we talked about different types of cell transport, and we talked about it again when we talked about neuron transport, the same exact sodium-potassium pumps. And they're going to start working. And remember that the sodium potassium they're antiporters, which means they go opposite directions. Okay, so you have the sodium will be pumped out. Okay, and again, out means you get to keep it in the body. And the potassium will be pumped into the tube, and that means that the potassium will be excreted, but the sodium you get to keep. Okay, so remember that the main point of the aldosterone is to increase the amount of sodium that you keep, that reabsorbed back into the body, and the potassium is just sort of sacrificed in order to get that happening. Okay, so I want you to see if you can write this out. So what was the specific mechanism of, so what is the purpose of ADH and how does it work? Okay, so I might write that out maybe. So the purpose of ADH is to increase water reabsorption, and it does it by inserting water channels or aquaporins into the collecting duct. Okay, so what about aldosterone? Aldosterone, you want to keep sodium. That's the main point. You keep that sodium. And then it does it by activating the sodium-potassium pumps in the distal and convoluted tubules, and not distal convoluted tubule and collecting ducts, and that's going to help actively take sodium out if you need more sodium. So remember, you're only going to secrete aldosterone if you want more sodium in the body. You don't have enough sodium. Okay, so here let's look at a little bit of a scenario, see how we can adjust those. So if you want more sodium, but you don't want the water to follow it. Okay, so you want more sodium, but not water. How are you going to adjust the levels of ADH and aldosterone? So if you want more sodium, you're going to secrete aldosterone. And if you don't want more water, you're going to decrease the secretion of ADH. Okay, so more aldosterone, but not ADH. That'll get you sodium, but the water won't follow it. Okay, so remember that the ADH only makes it more permeable to water, and so if it's less permeable to water, that just means that you'll take the sodium out, but the water won't follow it. Okay, that's the last little piece. See you later.